Let me discuss about multiple random variable. In many applications, it is important to study two or more random variables which is defined in the sample space. So in this module, we first consider the case of two random variables, their associated distribution and some properties. Now let me define a bivariate random variable, which is also called as joint random variable. Let S be the sample space of a random experiment, and let x and y be two random variables. So then the pair x comma y is called bivariate random variable or two-dimensional random variables. So in this module we focus on joint characterization of two random variables. So if the two random variables are discrete, we use joint PMF and joint CDF. If they are continuous, we use joint PDF and joint CDF. So we focus only on continuous random variable. Next, let me define a joint distribution function. So as we know, the distribution function of single random variable, so which is nothing but the probability of the variate x which takes the value less than or equal to x. So in the same way, we can have a bivariate distribution function or joint distribution function. So it is also called as the joint cumulative distribution function. So the joint cumulative distribution function of two random variable x and y is defined as the probability of the variate x takes the value say less than or equal to some a, which is a specified value of x, and that the random variable y takes the value less than or equal to a, which is also a specified value of y. So the distribution function of a joint random variables is denoted by capital F xy of x comma y. So it is given by the probability of the variate x takes the value less than or equal to x intersection y less than or equal to y, or we can also write it as probability of the variate x less than or equal to x comma y less than or equal to y. So always cumulative distribution with respect to a single or a multiple random variable is nothing much which takes the values less than or equal to here. I have listed a few properties of joint CDF. So 1 to 7 properties are the two-dimensional extensions of the properties of distribution function of one random variable, and the property 8 and 9 defined to be the marginal CDFs. So let me highlight the property 8 and 9, that is fxy of x comma infinity, the distribution function of joint variables where y takes the value infinity, so which is denoted by fx of x. So this is called as the marginal CDF of x, and property 9 is called the marginal CDF of y, that is fxy of infinity comma y which is equal to fy of y. Next, let us define a bivariate probability density function or joint probability density function for a continuous random variable. So the joint PDF is given by fxy of x comma y is equal to, which is a partial derivative, second order partial derivative with respect to x and y of the CDF of a bivariate random variables x and y. That is fxy of x comma y is equal to dou square by dou x dou y of the CDF of the bivariate random variables. So then the function f xy of x comma y is called the joint PDF of x comma y. So once we know the PDF of the bivariate random variables, so we can find the CDF also. So the joint CDF can be expressed in terms of the PDF as fxy of x comma y is equal to double integral from minus infinity to y minus infinity to x, the PDF of xy with respect to uv times du dv. So here I have taken the variables u and v because we have already x, y and y in the integrand. So the PDF of uv with respect to du dv. So this is how we can express the CDF in terms of the PDF. Once we know the PDF, we can obtain the CDF. Once we know the CDF, we can obtain the PDF from 1. Next, let me have properties of joint probability density functions. So already we are aware of the properties. The first two properties defines the fxy of x comma y is a valid PDF. The third property gives the probability of an event is the volume of the joint PDF over that event. That is, the probability of the variate xy can be computed between an interval x1 to x2, y1 to y2. So which is nothing but an event, which is given by the volume of the PDF. And the fourth property defines to be the marginal PDFs of x and y. Marginal PDF. It is given by fx of x is equal to single integral over y of the bivariate PDF into dy. So to obtain the marginal PDF of x, so we have to integrate the bivariate PDF with respect to y by keeping x as constant. Similarly, to obtain the marginal PDF of y, we have to integrate the PDF with respect to x by keeping y as constant. So with the above definitions, so let me define the independent random variables. So what do you mean by independent random variables? So when we say that the two random variables x and y are independent, so when we come to the CDF, if the CDF of the bivariate random variables is equal to product of their marginal CDFs, then we say that x and y are independent. And also, if the joint PDF is equal to product of their marginal PDFs, then also we say x and y are independent. Similarly, we can have the bivariate PDF with respect to the discrete random variables. So discrete means if the random variables x and y takes the finite values, say x1 to xn, y1 to yn, then double summation over ij pxy of xi yi is equal to 1. Then we say that pxy of xi yi is a PDF, and we denote this by fxy. Fxy is equal to p at x is equal to x, y is equal to. So this is the PDF with respect to the joint bivariate random variables when they are discrete. So let me have few examples on the PDF CDFs. Number 1, the joint PDF of two random variable x and y is given as fxy of x comma y is equal to c into 2x plus y for x lies between 0 and 2 and y lies between 0 and 3, 0 elsewhere. Then find the value of the constant c. So in this problem, we have given the joint PDF of two random variables, which is defined over an interval 0 to 2 and 0 to 3, elsewhere it is 0, from which we have to get the value of c. So as we know from the properties of PDF, in order to say fxy of x comma y is a valid joint probability distribution function, then always we should have double integral from minus infinity to plus infinity fxy of x comma y dx dy is equal to 1. This is the condition for the joint PDF, where the variables x and y takes the values or takes the range between 0 to 3 and 0 to 2. So the 0 to 3 and 0 to 2 are the subinterval of minus infinity to infinity. So in this interval, the PDF is given by c times 2x plus y dx dy is equal to 1. Now let us evaluate the integral on the LHS. So firstly, let us integrate with respect to x, then we shall integrate with respect to y. So c is a constant, take out c from the integral sign. So integrating with respect to x gives 2 into x square by 2 plus y is a constant. So y into integration of a constant is x, and evaluating this with respect to 0 to 2, we get the integrand 4 plus 2y dy. Next, evaluating between 0 to 3 with respect to y gives c is equal to 1 by 20. So for this value of c, the given function represent a valid probability function. Next problem. The joint PDF fxy of x comma y is equal to 4xy for x5, for x lies between 0 and 1, y lies between 0 and 1, 0 otherwise. Find number 1 marginal densities or marginal probabilities. Number 2 are x and y independent. Check whether fxy of x comma y is a valid PDF or not. Find one by one. So first let us show whether the given PDF is a valid PDF or not. So for which we have to consider the property. As we know the property, in order to say fxy of x comma y is a valid PDF, always we should have the condition double integral from minus infinity to plus infinity fxy of x comma y dx dy is equal to 1. So the given function is defined between 0 to 1, 0 to 1, substituting the integrand and evaluating the integral on the RHS between x and y. So we should get LHS is equal to RHS. So RHS is 1. So evaluating the integral on the LHS, we get 1. So therefore, this shows the given function is a valid PDF. Next, let us find the marginal densities. So as we know the formula, the marginal PDF fx of x is given by the marginal PDF of x denoted by small f. Okay, fx of x is equal to integral over y of the bivariate PDF fxy of x comma y with respect to dy. Okay, so formula, in the formula I have substituted the given bivariate PDF. Now let us evaluate this integral with respect to y between 0 to 1. So as we know y varies between 0 to 1 according to the given function. Take out 4x, which is a constant now. So integrating with respect to y gives y square by 2 between 0 to 1. Substituting the limits and simplifying, we get 2x. Similarly, let us find the marginal density with respect to y. It is given by fy of y, which is equal to integral over x of bivariate PDF times dx. So the bivariate PDF is 4xy. Since we have to integrate with respect to x, so x varies from 0 to 1. Evaluating this integral by integrating with respect to x, so it gives 2y. Therefore, we have found the marginal probabilities of x and y. So lastly, we have to show whether x and y are independent or not. Since we have found the marginal probabilities, so as we know the condition to check whether the bivariate random variables are independent or not. So the condition with respect to PDF is the joint PDF is equal to product of the marginal PDFs. So joint PDF is given by 4xy is equal to, we have computed the marginal probabilities of x and y. Substituting, we get 2x into 2y. So LHS is 4xy, hence we get RHS as 4xy. Therefore LHS is equal to RHS. Hence we can say x and y are independent because the joint probabilities is equal to product of the marginal probabilities. Next, coming to the next problem. The joint PDF fxy of x comma y is equal to c, a constant, where x lies between 0 to 3 and y lies between 0 to 3 and 0 otherwise. So now we have to compute a, what is the value of c, b, what are the PDFs for x and y, c, what is the CDF, joint CDF when x lies between 0 to 3 and y lies between 0 to 3, and what are the marginal CDFs, fxy of x comma infinity and fxy of infinity comma y, and lastly we have to show whether x and y are independent or not. So let me compute one by one. So let me write the given PDF. The PDF is given by fxy of xy is equal to c for 0, x lies between 0 to 3 and y lies between 0 to 3, 0 otherwise. So firstly we have to find the value of c. To find the value of c, so we have to use the property, that is the PDF is equal to 1 between minus infinity to plus infinity. So substituting the function fxy of x comma y, which is defined between 0 to 3 and 0 to 3, which is a subinterval of minus infinity to infinity. So therefore LHS is equal to this integral. So which implies double integral from 0 to 3 c times dx dy, since the PDF is a constant, so which is equal to 1 according to the property. Now take out c and evaluate the integral between 0 to 3 with respect to x and y. We get c into 9 is equal to 1, which gives c is equal to 1 by 9. So c is equal to 1 by 9 is the value of the constant. Next, let us find the marginal probabilities as usual. So marginal PDF of x is given by fx of x is equal to integral over y of joint PDF with respect to y. Substituting the joint PDF, which is c, and evaluating the integral between 0 to 3 dy. Since we have found the value of c as 1 by 9, substituting, we get 1 by 9 times 0 to 3 dy, where integration of dy is y, between 0 to 3 gives 1 by 9 into 3, which is 1 by 3. Similarly, marginal PDF of y, fy of y is equal to integral over x times the joint PDF with respect to x. So the joint PDF is c, and with respect to x we have to evaluate. So x varies from 0 to 3 according to the given function. Substituting and integrating with respect to x, we get the value of c is 1 by 9 into integration of dx is x between 0 to 3, which gives 1 by 9 times 3, which is 1 by 3. So fx of x is 1 by 3 and fy of y is also 1 by 3. So these two gives the marginal PDFs of the joint random variables x and y. Next, let us find the joint CDF. As we know the formula, since we have the PDF, so therefore we can easily find the joint CDF by considering the formula fxy of x comma y is equal to integral from minus infinity to y minus infinity to x fxy of uv into du dv. So substituting the joint PDF fxy of uv, which is c, zero to y, 0 to x, c times du dv. That is 1 by 9 times 0 to y, 0 to x du dv, which is equal to 1 by 9, 0 to y, integrating with respect to u first, next with respect to v, So which is equal to, we get integral, that is value of c is 1 by 9, 0 to y, u 0 to x, dv, which is equal to, substituting the limit x by 9, next integrating with respect to v, we get 0 to y, that is 1 by 9 xy. This is the CDF. So as x varies between 0 to 3, we can have 0 to 3 also. Next, let us obtain the marginal CDFs. So marginal CDFs are defined by fxy of x comma infinity is equal to fx of x. So as y varies between 0 to 3, so 0 to 3 is a subinterval of this minus infinity to plus infinity, right? So it is given by fxy of x comma infinity is equal to fx of x, which is same as fxy of x comma 3. So substituting in the definition of the CDF, right? So here I will show you. This is the definition, right? Here also we can use the interval 0 to 3, 0 to 3, no doubt, because x varies between 0 to 3, y varies between 0 to 3. So let me take the same definition to compute the marginal CDFs, where y varies between 0 to 3, x varies between 0 to x, fxy uv, okay, because fxy of x3, that is equal to, so we obtain as 0 to 3, 0 to x, fxy of uv dud, where the CDF is replaced by c. So 0 to 3, 0 to x, c dud. Let us first integrate with respect to u. So we have c times, c is a constant, take out that. So first integral 0 to 3, keep it as it is. Now we are integrating from the right. So integration of du is u between 0 to x gives x. Next integrating with respect to v, where v varies between 0 to 3, so which gives the value of fx of x as x by 3. Similarly, let us compute the marginal CDF of y, that is fxy of infinity comma y, okay. This gives the marginal CDF of y, which is fy of y, which is fxy of 3, which is same as 3 comma infinity, okay. There's 3 comma y, because the subinterval is 0 to 3, x varies from 0 to 3 here. So 0 to y, 0 to 3, okay. So in the definition, so I have substituted, and substituting for the PDF, which is c, and evaluating, we get y by 3. So lastly we have to show Rx and y are independent. So here we can take CDF or PDF. So let us take PDF. Joint PDF is equal to product of their marginal PDFs. If they are equal, then x and y are independent. Yes, obviously they are equal. 1 by 9 is equal to 1 by 3 into 1 by 3. So x and y are independent. Let us go to the next problem. A bivariate PDF for the discrete random variables x and y is 0.2 in terms of delta function we have given. Okay, always discrete PDF will be given in delta function, and CDF will be given in unit step function. Okay, so it is given between 0 to 1. Okay, that is 0.2 delta x delta y plus 0.3 delta x minus 1 delta y plus 0.3 delta x delta y minus 1 plus c times delta x minus 1 delta y minus 1. We call this as the impulse function or Dirac delta function. So we have to find one a, b, c, d and d. So let me find one by one. So first we have to find the value of c, since the given bivariate random variables are discrete. So to find the value of c, so we have to use this condition. It is enough to use because they are discrete. Okay. So double summation over ij fxy of xi yi is equal to 1. So summing up all the probabilities with over I and j, so we get 0.2, see 0.2 probabilities, 0.2 plus 0.3 plus 0.3 plus C, which is equal to 1. All the coefficients are the probabilities. 0.2 plus 0.3 plus 0.3 plus C is equal to 1. So if C is equal to 1 minus 0.8, which is 0.2. So the value of C is 0.2. A is over. In B, we have to find the PDF for X and Y, which we mean the marginal PDFs of X and Y, right? So PDFs means probability density function. So we have given a discrete, but we have asked to find the PDFs. So we have to use the integrals, obviously, right? So the marginal PDF is given by the formula fx of x is equal to minus infinity to plus infinity fxy of xy dy. So now substituting the given bivariate PDF, this is the given bivariate PDF. We have to evaluate this PDF over minus infinity to y. So I have written the next step directly. So what you have to do is you have to split this integral. Okay, split this integral, and you have to use the definition and the property of the derived function. So I have mentioned the definition and property on the RHS. That is integral minus infinity to plus infinity delta x dx is equal to 1. Where delta x is defined to be 0 for x is not equal to 0, infinity for x is equal to 0. And one property I have written, integral of f of t delta of t minus t naught dt, which is always equal to f of t naught. So I am using this property and this property and the definition, okay, to evaluate this integral. So splitting this integral into sum of the integrals, and we get, see, I'll take up the first term, integral of minus infinity to plus infinity 0.2 delta x delta y, where delta x delta y are unit step function, unit impulse functions. Okay, let us take out 0.2. So what is the value of, since we have to evaluate the entire integrand with respect to y, so delta x minus 1 acts as constants, right? So 0.2 delta x times integral of delta y between minus infinity to plus infinity, which is 1. Okay, plus, let me take up this second integral. Okay, 0.3 delta x minus y into, again, integral minus infinity to plus infinity of delta y, which is again 1. So it is 0.3 delta x minus 1 plus, let me take the third one, 0.3 delta x is constant. Okay, integral of minus infinity to plus infinity delta of y minus 1. So now to evaluate this integral, so we have to go with this property, this one, this property, where t naught is 1 and f of t is 1. So integral of minus infinity to plus infinity delta of y minus 1. Here I have written the result directly, so you just understand. Integral from minus infinity to plus infinity delta of y minus 1, where t naught is 1, and f of t is 1. So what will be the value? It is 1 only, right? So we can consider it as integral from minus infinity to plus infinity 1 into delta of y minus 1. Okay, so by applying this we get 1. Similarly, plus c is 0.3. So let us write c only, c into delta of x minus 1 is a constant. Again the value of this quantity, integral from minus infinity to plus infinity 1 into delta of minus 1 is again f of t naught, that is 1, because function 1 into delta of y minus 1, where t naught is 1 and f of t is 1, so therefore it is 1. So I have got this. Okay, so try to understand this step I've written directly with the help of the properties of Dirac function. Next, grouping the terms, grouping all the like terms by substituting the value of C, and finally we get the value of the marginal PDF of x as 0.5 times delta x plus 0.5 times delta of x minus 1. Similarly, let us find out the marginal PDF of y. See, here I have splitted the integral and I have shown, see here, 0.2 delta y is constant, since we have to integrate with respect to x. Okay, so the value of this integral is 1. In this case, here I have used the first property, here I have used the second property by considering here 1 into delta of x minus 1, f of t delta of t minus t naught, that is f of t naught, where t naught is 1 and f of t is also 1. Okay, so obviously in this case also the value of this integral is 1 and the value of this integral is also 1. And finally, grouping all the like terms by substituting the value of c, so we get the result as 0.5 delta y plus 0.5 delta of y minus 1. In C we have to find the CDF. So as we know, the joint CDF is given by fxy of x comma y is equal to integral from minus infinity to y minus infinity to x fxy of uv du dv. So as x and y varies from 0 to 1, 0 to 1, so here I have considered the first term of the given PMF or the PDF, that is 0 to 1, 0 to 1.2 delta u delta v du dv. So 0.2 is a constant, so delta u delta v are constant. So integrating with respect to u and v between 0 and 1 and 0 and 1, we get the value as 0.2. Next, let us compute the marginal CDFs of x. So as the given bivariate random variables are discrete, so we can go with the marginal CDFs with respect to the discrete random variables. So as we know the formula, already we have learned this in the single random variables. The CDF is given by fx of x when x is discrete, summation I is equal to 1 to n, the probability times the unit step function u of x minus xi. So now substituting all the terms with respect to the given function. So 0.2 probability 0.2 u of x plus 0.3 u of x minus 1 plus 0.3 u of x plus c is 0.2 u of x minus 1. So combining all the like terms or grouping the like terms, we get this. Similarly, marginal CDF of y, since it is a discrete, so in the same manner we have to compute by using the same formula, this formula. So in terms of y gives this, and finally we have to compute or we have to show whether x and y are independent or not. Since we have found the marginal CDFs, right? So let us find fx of x into fy of y. If they are equal to the given function fxy of x comma y, then we say that x and y are independent. So here when we compute the product is not equal to the given function joint CDF, joint PDF. So therefore x and y are not independent. So just go through the example 5 and try to solve example 6. So this is a maths example 4. Try to compare.